Yeah, efficient end-to-end entity linking for questions. So you may ask, why do you care about entity linking? So let me just walk through some reasons you may want to care about this. So first, if you use entity linking, usually can improve your question answering systems by a lot of margin. And it's also a very nice tool to build up your knowledge bases, or you can say ontology. And more importantly, you can also improve your chatbot. And in fact, these all three things are highly related. So entity linking is a very important topic if you want to implement one of these, and it will help you to build a more robust system. So what's special about this paper? It's a end-to-end linking, entity linking. Usually, entity linking need to detect the entity and link the entity to your database. They kind of things. It's like two stages model. But in this paper, they present a fully end-to-end neural network model to solve this problem, which is quite difficult to do. And it outperforms the previous state of the art by a lot of margin, 12% to 19% improvement. That's a lot. And more importantly, its inference time is even faster than the previously state of the art. By the way, I make deep learning explained video every week. So if you would like to receive more relevant videos like this, don't forget to subscribe. And your subscription is also my best encouragement to make more videos like this. So this work is a joint work from MIT, University of Washington, and Facebook AI. And this is the overview of this paper. So the question is, when did Shark come to the NBA? And Shark, who is Shark in this question? So you will first run a model to detect the entity. The mention here, Shark, is a person. At least you need to know it's an entity. Then you compare with your database. Your database will have a lot of entities. Let's say maybe 100 million entities. Then you run a similarity comparison. Basically, in this paper, they use in the product to make sure how similar this entity and this mentioned candidates are. Then decide. In the end, they say, oh, it's Shaquille O'Neal. It's an NBA player, legendary center Shaquille O'Neal. So there are two main steps that you need to do in order to perform end-to-end entity linking. First one is to detect the mention, and second is to disambiguate the entities, because one mention, they can basically mean a lot of possible entities, so you need to disambiguate those entities. Only one is true. Let's look at how they present entities in the questions. So you will first have the question, when did Shaquille O'Neal join NBA? Then firstly, you need to detect the entity in this question, and how do you represent the entity in this question? So basically, very simple. You use the BERT model, then you feed the whole question to the BERT model. Then after the BERT model, you will have the representation for each token. Right, so this is the way to represent a token in the questions. And how do you represent your entity in your database? Because in this question, there are only one. In this example, when did Shark join NBA? Only Shark, this token, is the entity that we want. It's only a mention. So in the end, we will only use the representation for the token Shark to represent this entity. But at first, we need to calculate the all representation for all token in this question. So we use this way to do that. And another part is, after we extract the representation of Shark, we need to compare to the entities that we have in our database. In this case, they use Wikipedia as their database. Then every Wikipedia page is an entity. So there's a entity, a page, Shaquille O'Neal page. So Shaq O'Neal. So how do we represent Shaq O'Neal in the Wikipedia? It's actually like this way. It's also simple. You use the title. You fill the title. It's a chunk of text, right? A list of tokens, and you also fill a description. The first 128 tokens of the description, and you use the some special token to separate the title and the description. Then you feed all this to the BERT model. Then the BERT model will come up with the representation for each token. Then you select the representation of the classification token as the representation of this whole token. So this is just how it works. The standard practice of using the classification token to represent the whole text input. And this representation basically means this entity. This is a vector and means this entity. Okay, so after that, we kind of know the entity representation. We know the question tokens representation. Then how do we extract the question, the mention in the question, like shock? How do we extract this token? How do we know this is the mention? Is a candidate. So basically, they train the three models. First one is just to extract the start, the entity start. And another one is to extract the entity end. So this is very standard practice to extract the some entities in the question, or in the, like, if you're doing a lot of question answering, you probably use this way to extract the answer a lot from the passager. So this is just extract a start token of this entity. This is to extract the end token of this entity. And additionally, they also train another model, which is just the prediction layer on top of a BERT to extract the probability of this token being in the middle of this entity. So you have these three prediction layers on top of BERT. So it's not really like standalone model. They all share the same BERT encoder. Then in the end, you combine. How do you calculate the mention probability? How do you know this entity? Let's say Apple Computer Company. So you will, the token of Apple Computer Company. Apple is the star of this token. So if your model is like properly trained, the probability of Apple being start will be really high, and the computer is like in the middle. Apple computer is in the middle, so the computer will of being middle of the entity will also be very high. Apple Computer Company, the company is in the end, so the company, this token of being the end of the entity will also be very high. So you kind of to sum all the probability up, the probability of being the start of the entity, of being the end of the entity, of being the middle of the entity, you sum all them up, then you have the probability of this mention probability. So you run this through your old question. In the end, you will be able to extract the mention. So back to our example, when did Shaq join the NBA? So Shaq is an entity, will be extracted here if your model is properly trained. And another step is to do the entity disambiguation. And how do we do that? Firstly, we need to find out the representation of the question of the entity. In the Apple Computer Company example, we have three tokens: Apple Computer Company. Then how do we have the three vectors for each token, right? We have three tokens: Apple Computer Company. How do we kind of concatenate or aggregate these three tokens to one representation? So it's very simple. You just do the average. You average them. You average them. So you have the representation of the entity Apple Computer Company. Then you do the inner product with your Wikipedia your Wikipedia entities here, which you use the title and the description to get the representation of this entity, and you do the inner product of them. So if the inner product is higher, it means they are very similar, and more likely this entity is the one you find in the Wikipedia. So if this you use the Shaquille O'Neal's page as an entity here and do the inner product with the Wendy Shark join NBA, the token shark, the entity shark, then you will have very, very high similarity. But if you use another shark, maybe the shark maybe in some financial services or military services, then probably will be low. So this is the second step. And in the end, you will do the likelihood distribution over all entities because you don't know what entity is possibly be. So you need to do this kind of similarity, make sure to all your entities in your database. If you have 1 million entities in the Wikipedia, you need to do this 1 million times. It's a softmax basically, and you will select the one who has the higher probability. But in practice, you will probably not do this like likelihood over all entities. You will definitely use some trick to cut off certain entities that's highly unlikely. You only do the distribution over those likely entities, but which I will not cover here. So this is the basic concept of doing entity disambiguation. And how do you train this model? Because before you train the model will not really give you a good result, right? You do the inner product, but how do the model know the entities are similar? They in the Wikipedia and in the question, they're supposed to be high similarity, right? The inner product is supposed to be high. The model don't know. The model just doesn't know. Okay, so that's why you need to do the training. And so firstly, we need to have mention detection loss. The first is mention detection, like 2 steps. Mention detection, entity disambiguation. So mention detection, we need to write a loss function. So the loss function is pretty simple. We have the golden mention, which is the positive example. If the I and J is the goal mention span, it will be 1. If it's not, it will be 0. So you write your loss function here. So let's suppose we are extracting something that's in the goal mention span, then this will be 1. So you want to maximize the probability of this golden mention being extracted, right? Then if this golden mention is this span is not a golden mention, let's say Wendy Shark join NBA, and your span is first token when, and when is obviously not the entity, so it will be not the golden mention, so it will be 0. This ij will be 0, so be 0. This will be this term will be whole be 0. Then this will be 1. Then this will be the log only this term, because this will be 1, right? So you want to minimize this probability, because it's not right. It's the kind of negative cases, so you need to minimize the log probability of this negative case being extracted. So this is your loss function. I think quite straightforward. If you don't understand it, pause the video and think about it. You understand that, and you do a normalization here. Okay, then second step is entity disambiguation. And how do you do that? You basically want to, let's say E is the goal entity corresponding to your mention, right? If this is the goal entity, you definitely want to maximize this log probability, because it's a loss function, so you put a minus here. So you basically want to minimize this loss function. Then basically that means you want to increase the log probability of this entity. And how do you increase the probability? You want to increase the value here, which means the inner product need to be as big as possible, which is the biggest is definitely 1. Then you jointly train this model. How do you jointly train? Jointly train this model. You sum up this loss function. The whole beauty of this paper is how they write the 2 steps loss functions, the whole training end to end. Yeah, it's like, how do you do the 2 seemingly discontinuous actions, once detection, once entity disambiguation, into the one end-to-end neural network? It's really, really very beautiful. Okay, so let's look at the data sets. They perform these experiments on these 2 data sets. In fact, the original data set, Web BSQ, Graph, and the GraphQ, didn't have the boundaries for entity mentions. So they annotate the entity mention boundaries on these 2 data sets. So extend the data set. And this is some statistics. You have a number of questions and entities in the question. So basically, one question on average have more than 1 entities. And this is the result. Okay, so let's look at the first row. First row and second row, the difference between them is, one is to use the WebQSP database as a training data. Because as I mentioned, when you train, you need to have the database that contains a lot of entities. They use this to train as their entity database. And second row, they use Wikipedia as the entity database to train the model. And the third row is they combine these 2 databases into one and doing the training. Okay, so let's see if ELQ is this paper's model. Entity linking for question. If you train on the WebQSP data and evaluate on the QS data, then you have the better performance than you just train on the Wikipedia data, which is understandable. It's very reasonable, right? And if you combine these 2 data sets as a database in the training, then you have 89% F1 score, extremely high, which is extremely high. And the precision recall all is the highest ever. And yeah, the evaluation metrics here, you need to detect the entity and also link the entity to the database correctly, so it will be counted as correct. And definitely that's a little bit tricky there. As for detecting the entity, as long as there's overlap, then you will be counted correct. So that's some details you probably want to check in the paper. But I just want to tell you this end-to-end evaluation. You need to detect and link it correctly. Okay, so there are 3 baseline models. The first is VCG, which is previous state-of-the-art on the WebQSP dataset, WebQS dataset. And also another is TechMe. TechMe is a non-neural network based model, so it's very fast, but in terms of accuracy, is much lower than neural network based model. And the Blink is a entity disambiguation model, so it basically couldn't detect entities in the first place. And in order to do some comparison, the authors trained the BERT-based entity extraction model, basically NER models, as their first step is the entity mention detection model for the Blink. So they combine BERT NER model and the Blink as one. But the previous state of the art was this one. So let's just look at the previous state of the art, how it performs on the WebQS QS dataset. It has actually 74% F1 score. Then the proposed model ELQ has like 12% higher F1 score than that. So it's a huge improvement. And if you train on the Wikipedia data, because Blink is actually just trained on the Wikipedia data, it's only comparable in this case. Blink has actually 80% inference score. Actually, it's quite good. But proposed model ELQ has 3% inference score, higher than Blink. Okay, so let's also look at what happens if we just evaluate the dataset, the models trained on the WebQSP and or trained on the Wikipedia data on the GraphQ dataset. And the VCG has a very poor F1 score, 39%, and the proposed model has a better generability. It's almost 20% for a score higher than that. That's pretty cool. And if you compare to Blink, it's also much stronger than Blink, outperformed Blink by 6%. And by the way, this is not a previous state of the art. It's combined two models. So this VCG is truly previous state of the art. And if you combine both data sets, the proposed model can perform really well, almost 90% for score, and the 70% for score on another data set. And zero-shot learning, it did not fine-tune on GraphQ dataset at all. That's a super amazing result. And this field, the entity linking, end-to-end entity linking, it's still emerging field. So I believe there will be more and more studies about this in the future. It's pretty exciting. And the non-neural network-based model is very widely used in a lot of QA systems because you don't need to train too much. And more importantly, you just, it's very fast. So in terms of number of questions, they can be processed in 1 second. It's really fast. But the proposed model, ELQ model, end-to-end entity linking model, is actually also not too bad. It's 2 times faster as Blink, and it's 3 times faster as previous state-of-the-art VCG. And even in another dataset, GraphQ, it's almost like 5 times faster. It's super fast. And they did some ablation tests. Why it's so much faster than the other neural network models? The key component, the key contributors is actually the end-to-end, because previous models like VCG, it requires 2 steps. And in this model, they just completely end-to-end. So that's why it's has such performance, and it's just 70% slower than the non-neural network model. But in terms of performance, it's almost not comparable. This neural network, this TechMe model is very poor in terms of F1 score, right? Okay, so that's the experiment result, and this is just runtime. It's 2 times faster than Blink, and 1.5, 2 times faster, slower than Tech model. But it's not too bad already because it's not neural network model, right? And they also perform because to really prove their system is really useful, they need to use that in the more real data set. So they perform this on the real QA system. There's QA, 3 QA data sets. Then the QA data set, basically they use an entity. It's a GRetriever system. The GRetriever system need to, if you want to run the GRetriever system, you need to have the entity linking component in that. And previously, the standard practice is to use a TechMe model plus GRetriever system. And now they replace the TechMe model by ELQ, they train on Wikipedia, and ELQ, they train on a QA dataset. I think it's combined both. Or just a single one. You probably want to check with the paper. And after that, you can find out the ELQ model outperform the TechMe plus GRetriever dataset by 6% accuracies, 4% accuracies. And for this one, the TQA dataset didn't really have a significant benefit. But in general, it improved the dataset, the end-to-end, the question answering models accuracy by on average maybe 2 to 4% That's actually quite a lot. So that's kind of opened the door of end-to-end entity linking research, and it's probably will bring up more other studies on this in the future. I do looking forward to that. And a summary of this paper is this is a very rare end-to-end entity linking system, a neural network based, and it outperformed the previous state-of-the-art by a lot of margin, 12% to 19%, and it has a much faster inference time compared to other neural network model, and it also improves QA systems by 0.4% to 3%. That's on average maybe 2%. That's actually 2-3%. That's significant in terms of a QA end-to-end system. If you enjoyed the video, give it a like, and don't forget to subscribe for more relevant deep learning videos like this. And other than that, take care. Until next time.